Welcome to the Daily Challenge. I'm your coach, Po-Shen Loh. So I hear you're interested in math counts. Math counts is how I first discovered that math was really interesting. It was the first time that I found myself trying to do questions where I really didn't know how to start. And that's fun. It's actually much more fun to do questions you're not supposed to be able to do, because if you can't do them, you weren't supposed to be able to do them anyway. But if you can do them, you feel really good. Also because sometimes you are the one who invented how to do it. This is a mock math counts exam. What that means is that I sat down and I looked at several previous years of math counts to see what kinds of math might be covered. And then I wrote some very interesting questions for you to play with. Each of them is designed to teach an interesting concept in addition to being good practice. After you're done working on these problems, go and look at the solutions, because in the solutions we'll also teach lots of interesting mathematics. And there will also be a video explanation at the end of one of the interesting problems. Are you ready? Give it a go, and I'll see you in a bit. How do you do a question like this? At the beginning, it looks like there aren't that many dots. So maybe we can just draw all of them and count. Here's one. Here's a second one. Here's a third one. And you quickly find out that if you try to do this, it looks like a bit of a disaster. It actually will be a big, huge mess because there are lots of different ways to connect 3 points to make triangles. So it's actually not possible to count it just by drawing all of them. And when you see the answer, you'll find out that drawing all of them would also take forever. Instead, we need to find a more systematic way to do this. When you're looking for systematic ways in order to count all of the triangles, it can be helpful to maybe try to break your triangles into some different types. For example, one way to try to be more systematic is to try to count the triangles that have only one vertex in the top row and 2 vertices in the second row. And then we could multiply that by 2, because the number of triangles with 1 vertex in the bottom and 2 on top should be exactly the same by symmetry. Symmetry is one of the most useful things that you can use when you're trying to do a combinatorics problem. But there's also more symmetry. If I'm going to say that I'll take 1 vertex in the top row and 2 in the bottom, then maybe I should just count all the ways that I can draw a triangle using the top left vertex and 2 on the bottom, maybe like this. And then I could take that answer and multiply it by 5 to know how many ways I could take any of the 5 vertices on top and 2 of the vertices on the bottom. So this is a multiplication method. There is actually a very useful combinatorial trick that you can use to do this counting, but I want to motivate it. I want to show that even if you didn't remember it or you didn't know it going in, you can still do this question. You see, if I'm trying to find all the ways to take 1 of the vertices on top, the top left one, and 2 of the vertices on the bottom, I'm being really systematic. I know these don't really look like triangles, but that's because if they really were triangles, they would all overlap and I wouldn't be able to see anything. But you see, here, I can see that if I use the bottom left vertex, then I have 4. how about the number of triangles that use the next point and don't use the leftmost bottom point? Let's count those. I'll erase everything. I can have this one. I can also have this one. And I can have a third one. Again, these don't really look like triangles, but that's just because I'm trying to draw them in a way that I can tell them apart. I have 3. Do you see a pattern? In combinatorics, there are often patterns, and patterns are really useful. What you can see, perhaps, is if I want to know how many triangles use the top left and this point, but don't use any of these points, then that will just be 2 more. It would either use this edge and the top left, or it'll use this edge and the top left. So I should add 2. Next, how many triangles would use this point and the top left point and none of the left ones that I haven't yet counted? Well, there would just be 1, the one that uses this edge and the top left point. And I don't have any more because I can't just use this point and use none of those. So I see this pattern, 4, 3, 2, 1. I know perhaps you have a faster way of doing this, but I want to show this just because it also shows how patterns arise in combinatorics. So now what did we just count? We counted the number of triangles in total that use the top left point, and that number is 4 plus 3 plus 2 plus 1. 4 plus 3 plus 2 plus 1 is 10. And 10 is exactly the number of triangles that use this point on top and 2 points on the bottom. Okay, so how many triangles are there then that use any one of these 5 points on top and 2 points on the bottom? That would just be 10 times 5, which is 50. And these are the triangles that use 1 point on top and 2 points on the bottom. And finally, remember what we said at the beginning was that there are also triangles that use 1 point on the bottom and 2 on the top. So I need to take my 50 and multiply it by 2 to find how many ways there are to make any triangle using points on the top or the bottom. And so the answer is 100. That would have been no fun if we wanted to list all of them out. Now, I want to talk about other ways that you could do this that actually introduce or review some useful formulas in combinatorics. But I wanted to show first that you can always do things by brute force. You see, if I look at what I was really doing here, the hard part was to find out how many ways I could choose 2 of the bottom points to be my bottom points. That's called 5 choose 2. We always write it this way, and if you take our online course, we will go into this in extensive detail. But 5 choose 2 counts the number of ways to choose 2 things from 5 things. And we go into this in great detail in our online course, so I'm actually not going to go into it in great detail here. But there's an easy way to count how many ways there are to do this. It's a nice formula. The way it works is you say, I have 5 things to choose from, so there are 5 ways to choose the first thing. And then after I choose the first thing, I have 4 things left. Think of those points on the bottom row. after one of them has been picked, there are 4 ways to pick the other point. And so the answer is 5 choose 2 is just 5 times 4, right? But if you remember, last time there were 10 ways to choose 2 points on the bottom to be those 2 points on the bottom of the triangle. So I should obviously divide by 2, right? But why? Well, if you go back and look at the picture from before, what is 5 times 4 counting? Well, one way that's counted is picking this point and then this point. But another way that's also counted is first picking this point and then picking that point. And both of those are the blue triangle. So I've double counted the blue triangle because I could have counted it one way or in the other order. And so I need to divide by the number of ways I could reorder these 2 choices that I'm making. And bam, that gives you 5 times 4 divided by 2, which is 10. And in one shot, you find out that there are 10 ways to choose 2 things from the bottom 5. That could save you a lot of work. You see, in this problem, we could have just gone straight to the picture and said, I want to know how many ways there are to pick 1 point on top, that's 5, multiply by the number of ways to pick 2 points from the bottom 5, that's 10, multiply them together, and then times 2, because I can have 1 point on bottom and 2 on top instead, bam, 100. So that's another way of doing this question. But it turns out there's still another way too. And that other way practices another kind of choose. Let's look at the picture again. A triangle is picked by choosing 3 points. So shouldn't the answer just be 10, choose 3? Because I could just say, let's find all the ways of picking 3 points from the 10. What would happen if I tried to do this? Let's first calculate it and see if it's right or see what we have to change. 10 choose 3. If I want to choose 3 things from 10 things, again, as we talk about extensively in combinatorics here, there are 10 ways to choose the first thing. And then after that's gone, there are 9 choices left for the second thing. After that's gone, there are 8 choices left for the third thing. As we know from before, we better divide because maybe we chose the same set of 3 things in more than one way. But this time, you don't divide by 2. What do you divide by? Here, you divide by the number of ways that you could rearrange the order of your 3 choices. Just like how before, we divided by the number of ways to rearrange the order of our 2 choices, either this way or that way. If you have 3 things, there are a lot more orders you can make. I just can't put my fingers in all of them. It's kind of hard. But if you work that out, the number of ways to rearrange 3 things in order is 3 ways to decide which of the 3 things comes first in the order, times 2 ways to decide which of the other 2 things comes next in the order, times 1 way because there's only 1 thing left to put in the order. And that's 10 choose 3. How easy or hard is this to calculate? You just cancel. 4, 3. And so the answer is 120. Oh no, we know that's not right. And the reason that's not right is actually because you can't just say, pick any 3 points. In fact, this problem is here to show that if you wanted to use choose 3, you shouldn't just take 10 choose 3. The question says we need to be very careful not to let the 3 points be in the same line. How could that ever happen? There are only 2 types of ways that could happen. 3 points in this line or 3 points in that line. So in this question, we actually have to subtract the number of ways that you might accidentally have picked all 3 of your points in the same line. How many ways could you do that? Well, there are only 2 lines that could have caused that to happen. So I actually need to subtract 5 choose 3 and another 5 choose 3. Because 5 choose 3 is the number of ways to pick 3 points from the 5 points, whether on the bottom or on the top. 5 choose 3 by the same formula would be 5 times 4 times 3 over 3 times 2 times 1. But as we also see in this course, it's easier if you ever see yourself calculating something like 5 choose 3 to instead calculate 5 choose 2. And that's because these two are the same, because if I want to know how many ways there are to pick 3 things from 5, that's the same as finding the number of ways to not pick 2 things from 5. That's 5 choose 2. And that's a smaller calculation. That's just 5 times 4, we already did that, divided by 2 times 1, we just write a 2, that's 10. And so the answer to this question is also just 10 choose 3 minus 2 times 5 choose 3, which we've already seen is 120 minus 2 times 10, which is 100. These 3 different ways of showing how to do this question show how rich of a subject combinatorics is, and also show how rich of a subject this kind of math is. You see, you're able to think through your own way to solve the question, whether it be brute force, finding a pattern, or the method with choosing 2, which involves symmetry and multiplication, or this method involving choose 3s, which involves subtraction. If you learn math by trying these hard questions where you have to invent your own way instead of just relying on a method, you yourself will become really, really good at looking at any math problem and figuring out how to do it, whether you have seen it before or not. If you liked this way of learning math, we have an entire series of courses which walk you through and teach you how to develop this mathematical thinking, all while playing with the kinds of questions that you might see in math counts like this, or other math competitions, or elsewhere later in your journey of learning math.